Okay, so I want to talk very briefly about the energetics of solubility. Actually, just kind of whether things mix at all or not. And I want to introduce a very, very simple model. And what we'll be able to find is that just by looking at the Gibbs energy of mixing for a real system, we can predict that two phases form. And everything, again, let's recall, my type, okay, great. Let's recall for an ideal mixture, for ideal mixtures, delta S is positive, always. It's entropically driven. And if it's ideal, the enthalpy of mixing is 0. Right, which means that the Gibbs energy of mixing is equal to mean T delta S mix, which of course is less than 0. So mixing is spontaneous. No heat is exchanged other than through entropy. Okay, so this applies to, what was I going to say? This applies to gases, ideal gases, and real gases near standard conditions. But it also applies to liquids as well. Applies to some liquid mixtures. All right, and I'll show you some examples of where this works and where it fails. And the idea, again, is that the value of H mix depends on the relative, attractions between AA, BB, right, the likes and likes, and AB. Right, so if AB is stronger than AA, or BB, just as a reminder, I think we kind of came to this conclusion last class, H mix is going to be less than 0, which makes the mixing more spontaneous, right? It makes Gibbs more negative. And if AA, BB is stronger than AB, then enthalpy of mixing is going to be greater than 0. Right? And so in this situation, mixing is always going to be favorable, right? Because entropy is already positive, enthalpy is negative, so Gibbs is going to be more negative than usual. Right? That's a good thing. But here, if the system's endothermic upon mixing, well, depending on the temperature, delta H might be greater than minus T delta S, and that you end up getting a positive G, right? So it depends on the value of H mix, whether you get weird mixing effects or not. And that's kind of where I want to go today for the first half of the lecture. But I want to give you two examples of what I mean by ideal mixtures with gases, with liquids rather. So I want to look at two different situations. So the first one we're going to look at is an ideal mixture of liquids. We're going to ignore gases for now. And this isn't always true, but in general, like components, or let's say not similar components mix ideally. So if your two components of your mixture kind of look the same, feel the same, then they tend to mix ideally because their AA-BB attractions are similar to AB. So a great example of that is mixtures of benzene and toluene. Right? And these, of course, don't look all that much different. The only difference is one's got a methyl group and one doesn't. And these tend to mix ideally. And so the way that we often look at measuring ideality in liquids can be done in a couple different ways, but a really common way to do it by monitoring vapor pressures of each component. So the idea is that we have a flask or some container, some sealed container of our mixture. So let me draw that in two different colors. We got a little bit of benzene, a little bit of toluene in here. And what we're going to monitor is the components of the vapor on top of it, right? So you're going to have some gaseous molecules float in your sealed container, especially for things like benzene and toluene, which are fairly volatile. And we're going to measure the partial pressure, which we could call P. So for instance, PA and PB, right, for different components A and B, right, A and B in these colors, whatever those components are, and ideally, PA, the vapor pressure of A is going to be the vapor pressure in standard state of that molecule times its mole fraction. Right, so if you take pure benzene, you can measure how much vapor pressure it should be. If XA was 1, and then if you dilute it by half with something that mixes with it ideally, then the vapor pressure you're going to read is half that. Right, that's ideal. That's an ideal mixture. Right, that the partial pressures are dependent on the mole fractions of the components of the vapor above the liquid phase. Right, so what we can do is monitor. We can measure. Okay, that one's dead. I had a feeling that one was going to die today. Well, what we can monitor is plot as a function of, let's say, X benzene from 1 to 0, 0.5 and 0. Let me make sure I have the values for these right. And then I'm going to measure vapor pressure of each component in torr. That's what my data's in. And let me just give you some values to give it some sense of scale. 100, 150, and 50. Okay. And then I'm going to let benzene, I'm going to let benzene, let me try to do two colors that are rather distinct from each other. Benzene will be red, and toluene will be green. And what I want to do is I want to measure the vapor pressures in our mixture as a function of the mole fraction. And so if we have pure benzene, right, we're on right here, mole fraction of 1, then the vapor pressure of the mixture is just benzene's vapor pressure, which is about 170. We'll put it right here. And then, of course, if there's no benzene, then the vapor pressure of benzene is 0, so that's the other point. And again, the vapor pressure is linear in the mole fraction, right? So as a function of mole fraction, you just draw a line ideally, like this. And then for toluene, pure toluene has a vapor pressure of about 75. And of course, at 0, toluene, the vapor pressure is 0. So the ideal line should look like this. And then I'll write the total. The total in purple will be the sum of the two, which is like this. Right, so this is total. This is benzene. And this is toluene. And when you go and measure it, right, these are the ideal curves. This is assuming ideality. And then when you go and measure it, what you find is that, in general, this works pretty well. I'll draw it kind of like, let me draw this in dash, sorry. So the benzene one, I think, if I remember correctly, looks a bit like this. Like that. And toluene looks like this. And so the total adds up together, basically. All right, so benzene and toluene, they have very similar attractions to each other as they do to themselves, and so they just add together exactly like you would expect. And the enthalpy of mixing these two is pretty small. All right, so they add together very nicely. But we can look at a case where things don't measure nicely. So I think the example I use is, acetone. So now we're going to look at acetone versus carbon disulfide. So acetone is a somewhat polar solvent, and carbon disulfide is not. It doesn't have a dipole moment. It's not very polarizable. It's a pretty non-polar solvent. Right, so I would call this polar, and this is nonpolar. So they, in fact, don't add together in an ideal case. So if I draw a similar plot, so I'm going to plot the mole fraction of carbon disulfide. And again, let me make sure I get my vapor pressures right. This runs from 500 to 0. So this is vapor pressure. We'll set this to 2. It's 300, 400, 200, 100. Okay. And then we'll do the same colors again. This will be red. And this will be, and carbon disulfide will be green. And the vapor pressure of pure acetone is actually quite high. It's a very volatile molecule, about 250. And of course, at no acetone, it's 0. So ideally, acetones, that's not a very good plot. Sorry. Close enough. Close enough. So this is the ideal acetone. And then carbon disulfide has a vapor pressure of almost 400. So carbon disulfide's vapor pressure purity is 0 there, and then down here it's 0. And there's no carbon disulfide. And so the curves would look like that. And I'll draw the total as well, the ideal total. These are, again, ideal. These are not real. Ideal, the total will look like this. Okay, and then you go and do the actual measurement, and what you find is that in dilute solutions of dilute solutions of carbon disulfide, well, let's start with the acetone. So in concentrated solutions of acetone, the system actually experiences a lower vapor pressure than you would expect, and then in dilute solutions it increases a higher one, like that. And carbon disulfide always experiences a higher vapor pressure than you expect when mixed with acetone. Like that. And so the total that you expect, in fact, is almost always positive. All right, so very different behavior. And we can rationalize this just using the idea of relative intermolecular attractions. So let's look at the limiting cases in our situation. Let's look, for instance, here. Let me draw it with a different color. So let's take a snapshot of our solution here. Well, this 0.2 maybe or something like that. And let's look at our snapshot of our solution here at 0.8. So we're looking at dilute solutions of carbon disulfide and acetone in concentrated, or dilute carbon disulfide solutions. Sorry. Woo, this is tough. This is acetone as the solvent and carbon disulfide as the solute, and this is vice versa. This is carbon disulfide as the solvent and acetone as the solute. And I want to let's look at the behavior and see if we can just kind of rationalize it on a physical basis, why we observe what we do. And so let's look at x of CS2 equals 0.2. Here we see that the vapor pressure of acetone is less than the vapor pressure of acetone times its mole fraction. And for carbon disulfide, it's positive. It's greater than. So PCS2, the vapor pressure of CS2 is greater than the standard pressure, CS2, times its mole fraction. Right, and the idea is that right, in order to mix in the liquid, you need to have good solvent-solute interactions. They need to be attracted to each other, right? You need to bind your solute into your liquid. But what we see here is that the acetone effectively kicks the CS2 out. Right? Acetone attractions are much stronger than acetone CS2 and CS2. Right? Acetone says I'd much rather be in the liquid phase bonded to my buddies that look like me instead of being bonded to or attracted to the CS2s that don't look like me. I don't like hanging out with them. So the acetone pushes the solute out of solution effectively, right? It says you're not attracted to me. I don't want you in the liquid form with me. So go into the gas phase, right? So CS2 has an increase of vapor pressure than you would expect ideally, because the acetone really doesn't want the CS2 in there, okay? And so that makes a lot of sense, I think, right? That the CS2 is just not a particularly good mixing agent, right? So anything that it can't bind with, it's just going to kick out. That solid is going to kick out that carbon disulfide solute. So now let's look at the opposite case. Here we have the pressure of acetone is greater. Vapor pressure of acetone is greater than what you would expect. And CS2 is also greater than what you would expect. So they're both out. Right, and the same logic applies here. You have carbon disulfide is your solvent here, so there's majority carbon disulfide. So most of the liquid is going to be carbon disulfide. And when you stick acetone in, acetone says, hell no, I don't want to hang out in here. This is not cool. So I'd rather stay in the gas phase. Right? So that's why, right, so acetone doesn't bond well with the solvent. So more exists in the gas phase. Likewise, some of the acetone is, of course, still in the liquid phase. Right? We only see a small bump in vapor pressure, which means there's still some in there. But that the acetone that's in the liquid kicks the CS2 out. So the CS2 also shows a positive deviation. So what little acetone is solvated also pushes out CS2 into the gas phase. Right, so The moment you put anything polar into carbon disulfide says, yeah, no, I ain't going to hang out in here. Right? It's not a reasonable energetic environment to be in. And the acetone deviation depends on whether it's the majority constituent or the minority constituent. Right? If there's a majority acetone, acetone will want to bond with itself in the liquid, which is why there's a negative deviation. And then when it's the minority in the liquid, it's going to have a positive deviation because it's more enthalpically favorable for it to just go into the gas phase and stay away from the carbon disulfide. Right, it's always easier for acetone and carbon disulfide to mix in the gas phase than it is in the liquid because the intermolecular attractions are much weaker in the gas phase. So that's kind of what happens. And so as you go through a variety of liquids, mixtures of liquids, you tend to have these kind of two extreme cases, right? In general, these both form one layer. Right? These are not separate phases. So in both of these cases, there is only one liquid phase. They still mix, but they don't mix perfectly. Right? That's why we call them a real mixture, right? So the delta G of mixing is still negative, but due to the fact that there's a little bit of enthalpic contribution, right? The enthalpy is positive when you mix these two. You end up getting a slight deviation in the vapor pressures, right? But these still mix. Now you could imagine that if we drop the temperature so much that T delta S becomes small, then maybe G changes sign and they separate. Okay? Right, so that's the important take-home point that I want to give is that in liquid mixtures, or any mixture really, that have delta H mix greater than 0, which means that AB is weaker than AA or BB. The magnitude of T delta S and delta H determine whether one or two phases exist. So you can imagine that at 300 Kelvin, these mix together just fine. Delta H is greater than 0, but there's enough entropy that delta G is less than 0 for them to mix. Right, so this is H is much less than T delta S, so delta G is less than 0. Right, so they mix, but they don't mix perfectly. Right, so you can imagine if we drop T low enough that delta G changes sign, and then they separate into two phases. Okay, and that's what I want to talk about. This kind of limiting case, right, where we are right on the verge between real mixtures that mix okay but don't show ideal conditions, and how we can go from that situation into situations where two phases separate. Okay, and there's a really nice, really simple way to look at the energetics about that. All right, and that's kind of what I want to tackle today. Okay, let's close up some things here. All right, so what I want to do is I want to come up with a model. So ideally, I'm going to write down a formula. We talked about this formula when we first introduced mixing, and I just want to reintroduce it because it's useful here. Is that for an ideal mixture, delta G of mix is equal to the number of moles RT times XA ln XA plus XB ln XB, right, for your two components A and B, right? And we showed that this is always negative, right? Because the lns are always negative because XA and XB are less than 1. So this is a negative, this is a negative, and so the whole thing's negative, which is less than 0. All right, so what I want to do is I want to add a non-ideal term to this. I want to make it non-ideal. All right, so what I'm going to introduce now is a new term, delta H mix, which is equal to a new parameter lambda times nRT times the mole fractions of the two, XA, XB. All right, so lambda here is a dimensionless parameter. And let's look at what the values could be. And lambda can be between infinity and negative infinity. Right? It can be any value. Okay. And I want to look at the limiting cases here. So when I add this, so when I do for a real mixture, bless you. Delta G ideal, delta G real, if you will, is going to be delta G ideal plus delta H mix. And we got to add that additional enthalpy. And just doing the algebra, you get nRT XA ln XA plus XB ln XB plus lambda XA XB. Okay. So notice again, remind you this term is less than 0, this term is less than 0, this term is greater than 0, and depending on the value of lambda, it's either positive or negative, right? So this is greater than 0 if lambda is greater than 1, right? So and it's negative if lambda is less than 1. So if lambda is equal to 0, this just goes away. We have an ideal case. If lambda is less than 0, then the delta G drops. It goes more negative, which means that mixing is more favorable, right? Because that would be a negative term. Delta G, the more negative delta G is, the more favorable a process is. It means AB is greater than AABB, right? It's attractive. It drops the Gibbs free energy, gives you more energy back. And if lambda is greater than 0, then AABB is greater than AB. Okay, so this is repulsive. This is attractive. And this is ideal. Okay, very simple. All right, so now what I want to do is I want to look at how delta G changes as we move lambda, as we modulate lambda, as well as temperature. So I've got this loaded up in Desmos. Sorry, I've blocked the screen for you guys. I apologize. But we'll come back to it in just a second. I just want to show you how this works. Right, so here I have the equation for delta G. Right, that's what's being plotted here in blue. The units don't matter so much here. I've divided delta G by a value just to keep it on the board so it's not a giant dip. But here I've made the attraction slightly repulsive, and I'm at about 300 Kelvin, right? So kind of a reasonable temperature. And what you can observe is that this has a minimum here at 0, or sorry, has one minimum. Right? And I want to write on the board just kind of a concept in physics in general. And I've mentioned this before. We'll come back to it. This is called the minimum energy principle. Which is that a system will relax to minimize its delta G value. All right, so it'll go to a minimum, right? So that's the equilibrium value. This is also the same as saying delta G wants to be as negative as possible. And by the second law, all that means is that delta S wants to be maximum. So when you see minima in your free energy, right, or minima in your energy, that's where the system's going to ultimately evolve in time. Imagine, for instance, just think of it in terms of chemical potential. Imagine we start at a mole fraction of 1, right? We have pure substance, and this is a reaction, right? As this is mole fraction of A, and A converts to B. As A converts to B, the free energy decreases, right? So the system wants to evolve in this direction. Think of it as a ball rolling down this hill, and if it goes too far, well, then the ball wants to roll back down, right? So the momentum of the trajectory of the reaction is going to ultimately lead to this minimum point, this minimum energy point, which we call a stationary point, right, where the derivative of Gibbs with respect to the variable is 0, right? And that's where the system will end up evolving, right? So what this shows us is that in this case, this mixture of these two liquids that are slightly repulsive at 290 Kelvin should evolve in such a way that they mix together at about 0.5. If you mix equal amounts of both, you end up right here. Okay, so this would mean that there's one minimum at one value of mole fraction, which means there's one phase, right? This is one phase, right? There's one minimum. But now let's look at what happens as I change the repulsion. So now I'm going to increase lambda to make it more repulsive. And what you can see is now the free energy is increasing, right? Delta G is now more positive. And notice how the system starts to the curve starts to flatten out. It's much more narrow, it's much more shallow here. And this is due to the fact that, and what this is due to is non-ideality. So if the curvature looks like a parabola, looks like a nice parabola, that's basically ideal. Ideal would be a parabola. And of course, this is no longer a quadratic function. It looks like a weird very large polynomial. It's very flat. This is due to non-ideal things occurring, right? So if you have an energy curve that looks like this, it's kind of flat at the minimum, that usually indicates that you don't have ideality, but it still forms one phase, right? There's still one minimum right in the middle. But you can see that that energetically, the system can be at any number of different mole fractions, and the energy doesn't change that much, right? So you would expect that there would be some non-ideality in this case, because in order for the system to move from the ideal point, which would be right here in the middle, you don't really gain or lose much energy, right? So it can kind of sample this entire region on a flat surface, and so you would expect that this would lead to non-ideal effects. And so if I keep cranking it up, look what happens. Right now I make them really attractive, and now there are two minima. Right? There's a minimum that's enriched in A, and a minimum that's depleted in A. Right? So the system, this part in the middle is no longer a minimum; it's a maximum. So if you put the system here, well, it's going to separate. Half the material is going to separate. Right? If you have a ball here, right? And depending on what happens, just randomly, you're going to have some of the balls fall into this minima and some to fall in this one, right? So on average, if the sample is thermodynamic and you're statistically measuring, right, things are happening randomly and statistically, you're going to have some of your mixture in this minimum and some in this minimum, right? And so one minimum is going to have enriched in A or depleted in A, and one's rich in A, right? So this is two phases. Right? You have two energetic minima with two different mole fractions, which means that you have two different phases. Right? There are two different stable phases. So let me leave it here, and let's look at what happens as I change temperature. Right? This is the same idea as your solid-liquid phase diagram. Right? You're going to heat it up, and as I heat it up, okay, well they're so strong that it doesn't make much of a difference. But again, if I kind of go to a kind of an edge case, right, you can see that there are two minima start to form here. And as I change the temperature, the system starts to flatten out a little bit more. As I increase the temperature, that starts to create more. But you can see as I make them more and more repulsive, the mole fractions at which those minima exist at get closer and closer to 0 and 1, right? So in this case, we have a very, very repulsive, right? A and B don't like the mix, and so the phases are primarily B and primarily A. Right? This would be liquid. This would be like liquid and water, or water and oil. Sorry. Right? But if I, for instance, cool it down and I get towards this is more like acetone and benzene, or acetone and carbon disulfide, there's barely one minimum, but there is still one minimum. Right, this is what that would look like. So you have one phase, but they mix in kind of a strange way. But if I take, say, water and something that's very soluble in water that likes to attract with water, right, where the repulsion is negative, let me lower the temperature a little bit so you can see it, right? You get a really nice parabola, right, a really nice quadratic function with one minimum, right? This is an ideal mixture. All right, so this idea of looking for minima in the Gibbs free energy as a function of some parameter, say the mole fraction, or when we get to reactions, we'll talk about the progress of a reaction, which is related to the mole fractions. We look for the places at which the Gibbs energy is a minimum, and those are the places where the system will evolve to in time. So when we search for this concept is universal. So for instance, so imagine you want to calculate a molecule, the structure of a molecule. Okay, and you don't know what it looks like. Let's look at carbon disulfide, for instance. Right, you don't know if it's linear or not. Right, so what you could do is, on a computer, you could say, let's calculate the energy of carbon disulfide as a function of its bend. Right, and what you'll find is that, again, you can fix that bend to any direction, any angle you want, and calculate the energy. Right, so let's think about this as a bend angle. And so you bend it, and the energy is high, and then as it starts to straighten out, the energy decreases until you reach a minimum when it's flat, and then when you go the opposite direction, it increases again. Right? And so the idea is that, again, the system wants to be at the lowest possible energy, so finding the minimum of the energy with respect to the bend angle of carbon disulfide allows you to calculate the correct bond angle for carbon disulfide, right? So anything in chemistry, anytime we want to find the result of some process, whether it be the structure of something, right, or the reaction, or the equilibrium of a reaction, or the phases and stuff, if we can monitor the energy as a function of one of the parameters that we can change, right, temperature or mole fraction or whatever, we know exactly where a reaction is going to lead to, or a process is going to lead to, because we look for the minima in a Gibbs energy. Molecules chemistry and all physics is not only lazy, but as messy as possible, right? Energy wants to be minimum, and entropy wants to be maximum. Okay? So that's a really, really good, useful kind of trick to remember. So it's for any process, the process will always converge to the minimum of the energy. Okay. What time is it? Okay, great. Any questions about this content? All right. Let me close this up. I don't really have a lot of time to start equilibrium right now. So you know what? Let's just finish early for the day. And on Thursday, we'll start equilibrium. We'll spend the whole day on equilibrium. All right? Everyone seems a little tired today, so let's just finish a little early. And then we'll start equilibrium on Thursday. So we'll stick on equilibrium for about, I don't know, it depends, probably 3 lectures. We'll probably finish equilibrium before Thanksgiving, and then we'll start kinetics immediately after Thanksgiving. And during equilibrium, we'll look at kind of traditional equilibrium, and we'll also do a little bit of electrochemistry as well. So we'll also look at it as applied to electrochemistry. All right, guys, have a lovely day.